Thank you, sir. So what is the speed of light? Off by a factor of 3,600. 186,000 miles per second. How do we know this? Measured it. How did we measure it? The first person to measure the speed of light was Galileo, or at least he tried. He had his assistant climb to the top of a hill with a lantern, and he went to the top of another hill with a lantern. They covered both lanterns with cloths. His instructions to his assistant were, when I uncover my lantern, you uncover yours, and I will time the difference with my pulse. His conclusion was that the speed of light was damn fast. Couldn't detect any difference at all. The speed of light really kind of remained a mystery until the mid-1600s, when we finally got some idea of the size of the solar system. And we looked at Jupiter's moons, and we could see Jupiter's moons revolving around Jupiter with this precision that we could not match in any other way. And then we noticed that in January, we would look at Jupiter's moons, and we could see where they were. And then in June, 6 months later, we would note that the timing was off by 16 minutes. Now, we know the diameter of the Earth's orbit. We know the Earth was 186 million miles further away from Jupiter in January than it was in June, and so we could detect the speed of light as taking 16 minutes to cross 186 million miles, or roughly 186 million miles a second, 186,000 miles a second. We've measured the speed of light a whole bunch of ways since then. What do we know for sure about the speed of light? What's its abbreviation? C. And how did it get that abbreviation? Who gave it that name, C? It was a funny guy by the name of Weber in about 1820 or so, and he did an interesting calculation. He divided the magnetic charge by the electric charge, without any numbers, in fact, just the units. He divided the units, and out came this velocity, which was 3 times 10 to the 8th meters per second, or 186,000 miles per second. He knew what it was. He knew it was the speed of light. Imagine the chills going down this guy's spine as he took these two well-known quantities, the unit of electric charge, the unit of magnetic charge, and out of them came the speed of light. He had no idea why. It took Maxwell about 50 years later to figure out why that was the case. Of course, we're not here to talk about that. Although I might go on talking about it for quite a while. We are talking about, are you a professional? How many programmers do we have here in the room? Everybody's a programmer. That's good. So are you a professional? Well, what is a professional? How do we define the term professional? A professional is someone who has a set of professional standards. Do you have those? Do you have a minimum set of professional standards beyond which you will not go? Are you able to look your boss in the face and say no, because that exceeds my professional standards? Are you calm under pressure? A professional we would expect to be able to deal with pressure. Are you calm under pressure? Imagine, for example, a lawyer in the midst of a heavy courtroom battle. This man is a professional. Is he calm in the face of the cross-examination? Is he calm while delivering his closing statements? Is he in control of the situation? That is what we would consider to be a professional. Are you one? What does it take to say no? What kind of courage does it take to look at your employer or look at your boss and say, what you are asking me to do is unreasonable? How many of you have been told what the estimate will be, rather than making the estimate yourself? And did you say no? If you did not say no, then were you behaving as a professional, or were you behaving as a laborer? Were you behaving as someone who simply takes orders regardless of how unreasonable those orders are? Let me make a point. We hire professionals because we expect them to know their job. We expect them to know their job better than their managers do. That's why we hire professionals. That's in some sense the definition of a professional. We bring people in who know their work. Now, managers are certainly going to make unreasonable requests. It happens all the time. By the way, it's some part of their job. They have a job to do. They've got to make sure certain things happen at certain times and come in within budget. So they are certainly going to ask for things that to us seem unreasonable. And the reason they do so is they want a fight. They want a battle. They want you to stand up and say, no, I can't do that. No. And then they say, oh, I guess that must be where reality is. How do you find reality in a negotiation? You don't find reality by a simple agreement where everybody says, oh, yeah, that seems reasonable. You find reality in a situation through stress, through a negotiation that often gets heated. And the professional is able to stand his ground and say, no, I'm sorry. That is unreasonable. I cannot do that. I will not do that. It would be unprofessional of me to try. So let's go back in time a little bit and hunt through our disciplines. What are our disciplines of professionalism? How did we get them? If we go back all the way to the 50s, what was programming like in the 50s? What did we do? We punched cards. We ran compiles that took a day. Right? We did, our largest programs were a few thousand lines. A 10,000-line program was 5 boxes of cards that weighed 50 pounds. It took a long time to get it into the card reader. Those days were interesting. Who was programming in those days, other than me? One guy, okay, fine. What did we learn in those days? Well, we didn't learn too much, frankly. It was mostly a bunch of code that we wrote, but we did learn a little bit about modularity. We learned that it's not the best idea to take and write one massive program. It's better to have several smaller programs. The idea of modular programming became important in the late 50s and the early 60s. What did we learn in the 60s? Well, we learned a little bit more about modularity. We learned a little bit more about breaking systems up into pieces. But even in the late 60s, our software was remarkably small. How big a program could you have on a machine that had 4K of words? I used to work on PDP-8s in the late 60s. And those machines had 4K of 12-bit words. You can't get much into that kind of machine. Who's got a laptop with them in here? So let's see, how many laptops do we have in the room? Several dozen. Each of those laptops is probably got 1, 2, or 3 gigabytes of RAM in it. Compare that to the 4K of a PDP-8. That's 1,000,000 times more memory than that PDP-8 had. We used to get real work done in PDP-8s. But now we've got these machines sitting on our laps, essentially doing nothing at the moment, that have 1,000,000 times more memory. And what was the cycle time of a PDP-8? It was 1.5 microseconds. The clock rate was 750 kilohertz. What is the clock rate on your laptop? It's probably 2 gigahertz, maybe 3 gigahertz. Maybe you've got 2 cores at 2 gigahertz each, 4 gigahertz. So the speed is a couple of thousand times faster than that PDP-8. A couple of thousand times the speed, a couple of million times the memory, and we're starting to talk about real issues here. Right? 1 billion times more power in your laptop, and there are dozens of them in this room. So the kind of hardware we have now is remarkably more than what we used to have, and yet, what kind of work do we do? When we were working in the 50s and 60s, what kind of code did we write? Who was writing in those days? Late 60s. Did you do Fortran? Did you do COBOL? Fine. And what do you write when you're writing Fortran and COBOL? You write assignment statements, if statements, while loops. What's changed? Nothing. We write more of them. We write them in different places, but we still write assignment statements, if statements, while loops. our technology, our software technology, has not grown at anywhere near the rate at the hardware technology. The hardware technology has multiplied itself by orders of magnitude. And we, software people, have improved our technology slightly, maybe. We've got some better tools. Our editors are better. But we're still writing assignment statements. We're still writing if statements. We're still writing while loops. What did we learn in the 70s? In the 70s, we started slightly to learn about structured programming, the idea that we weren't going to use goto, the ability of taking systems and breaking them up into procedures that had a single entry and a single exit. And we turned that into an entire industry. Structured programming, structured analysis, structured design. Consultants made fortunes on this idea. The word structured became equivalent to the word good. And so everything then had to be structured. We saw that again happen, by the way. It happened again with objects. It happened again with agile. It's going to happen with every new thing that comes along, because as soon as it gets equated with good, everybody has to be it. We also saw in the 70s the fundamental trifurcation. The fundamental trifurcation is the split of every concept into analysis, design, and programming. No concept since that time has survived that trifurcation. Anything that we come along with, whether it be structured or objects or aspect or agile or anything else, has to be split into three. There's object-oriented analysis, and object-oriented design, and object-oriented programming, structured analysis, structured design, structured programming. We have somehow decided that the world must be divided into threes. And oddly enough, we don't know how to define any of them. What is the definition of analysis? That's exactly right. No one knows. Right? Nobody knows the definition of analysis, and you can go and look at the books out there that talk about analysis, and you'll find that for every author there's a different definition. We don't have a solid definition of the term analysis. We do know that we're going to spend a third of our time on it, but we don't know what it is. The best definition of analysis is it's what analysts do. Right? But we don't know what it is beyond that. And so we now decide, okay, to further define analysis, we need to put adjectives in front of it. Adjectives like structured, adjectives like object-oriented. Can anybody define for me what object-oriented is? Again, we don't really know. It has something to do with inheritance, encapsulation. Maybe it's got something to do with procedures and data being close to each other. But when you push on this issue, no one has a definition, a solid definition for what this concept is. So then we take the two words and we stick them together, object-oriented analysis, and we make a term that is doubly undefined. We got very good at doing this in the 70s. In the 80s, we started learning about objects. Booch published his wonderful book, Object-Oriented Design with Applications. Who read that book? Object-Oriented Analysis and Design with Application was the second version of that book. Came out in the early 90s. Rumbaugh wrote his book. Bertrand Meyer wrote his book, Object-Oriented Software Construction. We started learning that you could subdivide systems into these object forms that had some kind of benefit. In the 90s, we started to learn more about design principles and design patterns. Who's got the design patterns book? Oh, yes, and who's read it? It's always good to read the books that you have. It's not all that good to just have it on the shelf. And the Design Patterns book is one of those books that really needs to be read. It is probably the most significant book written in the last 20 years. Not because it says anything new, but because everything in it is old. And it's been around the block a few times, and it's proven its worth. And then came the double noughts, the 2000s, the decade that's just ended. And something very interesting happened in that decade. The birth of Agile occurred in that decade. And it's not quite fair to say it was the birth of Agile, because Agile had actually been around for a while. It just didn't have its name. But in the year 1999 to 2000 to 2001, we started to see these ideas percolate up above the normal consciousness level. We saw extreme programming show up. We saw Scrum show up. We saw the Agile Alliance get formed. We saw this rebellion against the fundamental waterfall nature of things. How many of you are doing Agile development? Look at that. There's quite a few of you here that are doing it. More than 2/3, I would say. That's pretty startling. Even though this is an Agile conference, it's still pretty startling that we've managed to get that many people doing Agile. And in fact, the world is loaded with people doing Agile now. It is the thing to do. Agile has certainly crossed into the mainstream. It is the thing. It took 10 years to do it, but it did it, and that's pretty good. So the year of the 2000s, the decade of the 00s, was the year or the decade we learned about Agile practices. And if we assemble all of these ideas from the 50s, the 60s, the 70s, the 80s, the double knots, if we assemble all those ideas, we start to get a significant repertoire of disciplines, a significant repertoire of ideas that we could say define our profession. So I'm going to come up with an oath, something like the oath that doctors take, the Hippocratic Oath, for software professionals. The thing that doctors say in their oath is, first, do no harm. How do software developers do harm? What harm can a software developer do? Well, a software developer can do harm to the function of the software. So first, do no harm to the function of the software. We are paid to get software to do something. So how do we not harm the function of the software? Has anybody here ever released code they weren't certain worked? Giggles through the crowd. Of course you have, you fool. We're software people. We always release stuff we don't know works. That's unprofessional. You should know your software works. And you should know it at a very personal level. Do no harm to the function. That means you know it works. And you know it works much better than just having run it a couple of times and tested it and saying to yourself, oh, I think it works. You have tested it. You know that it works. You are willing to release it to someone else in the sure knowledge that your code works. Any other behavior is unprofessional. How can you call yourself a professional if you are willing to release a work product that you're not certain of? Now, of course, you're going to be wrong. Of course, there are going to be times when you think you've done everything you can, and in fact, some bug snuck through. But that's just because we're human. Under no circumstances should you ever release something if you're not certain, if you haven't done all the due diligence, if you have not tested it and made sure that it works. Now, someone will react and say, yes, but there are schedules. Believe me, I can meet any schedule in the world if I don't have to make it work. If my code doesn't have to work, name a date, I'll meet it. But if it has to work, well then, I'm going to have to be sure that it works. I'm going to have to do what it takes. What should QA find? Nothing. QA groups should find nothing. We should, as a development organization, release our software to QA. QA should do all of its tests and come back with a report that has a single character on it, 0. Now, of course, that's not the way it's going to work. QA is going to find things because we're human. We're going to make mistakes. But every time QA finds something, we should be going, how the heck did that happen? How did that bug get out? How did QA find this? And we should institute things to prevent that in the future. We don't want QA being the broom that sweeps all the bugs back to developers. We don't want developers acting like, oh, well, QA will find these bugs, so I don't have to worry about them. QA should find nothing. That's the only professional attitude to take. How do you make sure that happens? How do you make sure that QA finds nothing? You have tests. You run those tests. You run them all the time. You have automated tests, tests that you have written, unit tests and acceptance tests that you can run at the push of a button. This is part of the agile canon of practices, by the way. Things we learned from extreme programming and from Scrum. We don't write code unless we also write tests. And those tests will test virtually everything in the system. Every line of code will be covered by a test because we need to know that every line of code works. We expect to be able to measure our code coverage using a good coverage tool and get 90, 95% coverage. And we might accept that lower number, the difference, that final 5%, as just the coverage tool not being able to see certain lines of code. Some coverage tools have problems with catch blocks. Others have problems with code executed in other processes. Okay, fine. Maybe we'll tolerate that. But our goal is to have a suite of tests that we can push at the push of a button, we can execute. And those tests will show that our whole system works. And if those tests pass, QA should find nothing. In fact, we'd like QA to be part of the authoring of those tests. Because the real goal with QA is to get it off the back end of the process, move it to the front end of the process, where they are authoring the requirements and authoring the tests that must pass. We don't want QA stuck at the rear end of the process. That's a terrible position to be in. You cannot assure quality at the back end. You have to assure it at the front end. Do no harm. Do no harm to function. Also, do no harm to structure. How many of you have been significantly impeded by bad code? That's what, about 40% of you? The rest of you are lying. Right? Because, of course, we have all been impeded by bad code. We've all had the experience that bad code slows us down. Now, the question I'll ask you is, why did you write it? If you know this bad code is going to slow you down, why would you write it in the first place? And the answer to that is, of course, well, we didn't have time. There's deadlines, and we've got to meet the deadlines. Okay, so let me get this right. You have to do the thing that you know will slow you down in order to go fast. There is a deep contradiction here, deep within our own hearts. We can blame managers all we want for unreasonable deadlines. We can blame organizations all we want. But the real issue sits right here. If you produce bad code, you know you are going to slow yourself and everybody else down. If you produce the best code you possibly can, you know you're going to be going as fast as you can. There is no way to go faster by producing crap. You only go fast if you do the best you possibly can. So there's a fundamental rule here. The only way to go fast is to go well. So do no harm to structure. Now, the problem with that is that you're writing code and you're focused on getting it to work. And you're not focused so much on its structure. You're trying to get it to function well. And eventually you get the code to work, and then you think you're done. You're not done. Once you get code to work, then you have to go back and start cleaning it. Cleaning the messes you made, cleaning the mistakes you made, restructuring so that it's better. We call this refactoring, another one of the disciplines in the Agile canon. And we refactor our code and we clean our code until we believe it is acceptable. That is, it is clean. It does not have any mess in it. When do we do this refactoring? We do it all the time. Every hour, every couple of minutes. We write a little bit of code, we get it to work, we refactor it. We write a little bit more code, we test it, we get it to work, we refactor it. We're always refactoring. We never put refactoring as a line item in a schedule. No schedule will ever have a blob in it that says refactoring. And the reason it will never have that is because if it does have it, someone will cross it out. Refactoring is something we simply do. We do it all the time. We do it as part of our professional practices. We keep our code as clean as possible. In order to refactor, you must be able to change the code. The code must be easy to change. How do you make code easy to change? Well, we could talk lots about the design and the architecture of the code and why that's all important, but the real reason, the real way that you make code easy to change is by changing it. If you change your code frequently, you will put in the structures that make it easy to change. The changing of code makes it easier to change, which means that we've got to refactor all the time, constantly keeping the code flexible because we're refactoring it. And you say, well, yes, but if I do that, I might break it. How many of you have looked at a module on your screen, and your first look at it, you think, my God, this is a mess, I need to clean it. And your next thought is, I'm not touching it. Because you know if you touch it, you'll break it, and then it will become yours. So you think, nope, I'm not going to touch it, walk away from the code. That doesn't help you make changes to the code. We need some way so that we are fearless about making changes to the code, so that we are not worried about our cleaning breaking something. And how do we do that? How do we get to the point where we can make changes without any fear? Who's heard of test-driven development? Who's doing it? Okay, now this is an Agile conference, and I'm seeing about 5%, and that's extremely disappointing. Right? At other conferences I go to, I'll get as many as 50% of people doing test-driven development. So let me ask you, what's wrong with you? Why aren't you doing test-driven development? What has happened here that would prevent you from this, what I consider to be an essential discipline? So let me talk about test-driven development for a bit. Let's see what we know about this discipline. There are 3 laws to test-driven development, 3 fundamental things that you have to do. And the first one is highly controversial. In order to do test-driven development, you are not allowed to write any production code until you have first written a unit test, and that unit test has to fail. Now that right away sounds stupid. Right? What sane programmer would write a test first that fails and then make it pass later? But it gets worse. The second rule of test-driven development is that you are not allowed to write more of a unit test than is sufficient to fail. You can't just keep on writing the unit test. As soon as the unit test fails, you have to stop writing it and start writing production code. And not compiling is failing. So the instant the unit test doesn't compile, you must stop writing it and start writing production code that makes it compile. Now, think about this for a second. You're now stuck in a loop. That loop is maybe 30 seconds long. You write a little bit of test, a little bit of code. You write a bit of a test and it won't compile. You have to write a little production code to make it compile. You write a little bit more of a test to make it do something and it fails. You write a little bit more production code to make it pass. You're stuck in this loop that's maybe 30 seconds long. And then the third law comes along and says, yes, and not only that, but you're not allowed to write any more production code than is sufficient to pass the currently failing test. This makes you stuck in this funny little 30-second loop. Now, any sane programmer of any number of years' experience is going to say, well, that's just stupid. Why would I do that? That would be slow. It would be tedious. I know how to write if statements. I know how to write while loops. I don't need to write tests to prove that they work. I'll write the tests later if I have to write tests, but I'm not going to do this stupid thing of going around this loop 30 seconds. All right, fine. Imagine a group of people following these 3 laws. Pick one. Doesn't matter who. Doesn't matter when. Sometime in the last minute or two, everything they were working on executed and passed its tests. And it doesn't matter who you pick, and it doesn't matter when you pick them. In the last minute or 2 or 3, everything they were working on executed and passed its tests. What would life be like if we were never more than a few minutes away from a complete execution of everything? Passing. How much debugging do you think you would do? And the answer to that is not very much. You don't have time to get into much debugging because the bug you just created, if you did create one, you created in the last 30 seconds or so. Maybe the last minute, maybe the last 2 minutes. So the amount of debugging you're going to do is going to be very, very small. Now, as it turns out, that is a true statement. After I adopted test-driven development, I stopped major debugging. It just doesn't happen anymore. Oh, every once in a while I have to get into a debug session, but it's an order of magnitude down. How many of you are really good at the debugger? How many of you know all the hotkeys? You know, like do this key to step into and that key to step over and this one to set a breakpoint and this one to set a watch point. This is not a skill to be desired. We don't want you to be good at the debugger. We want you to be good at not using the debugger. We want you to be good at avoiding having to use the debugger. Now, I still fire up a debugger every once in a while, but it's nowhere near as often as it used to. I've forgotten all the hotkeys. And I don't stay in debuggers for very long. 30 seconds, a minute, 2 minutes, I'm in a debugger. I might set one breakpoint. I might go there and look and say, oh yeah, there's the problem. Because the problem occurred in the midst of a test, and I can set the breakpoint at the test, step into it and go, oh yeah, something stupid. Are there still long debug sessions? Yeah, but there's hardly, they're way, way down in frequency. Now, imagine that you could cut your debug time by 50%. I think, by the way, you'd cut it by a lot more than 50%, but just let's say you could cut your debug time by 50%. How much would that save you in coding time? And the answer to that is probably fairly significant. So just on that basis alone, test-driven development probably is a net gain. But let's explore the issue a little bit more. If you follow these 3 stupid laws, you will write dozens of tests every day, hundreds of tests every month, thousands of tests every year, and you will keep all of them, and you will run them all the time. Imagine hitting a button and watching thousands of tests run, covering your entire system, proving to several decimal places that that system works. How afraid are you now of making changes? You look at the code, you think, that code's kind of ugly. I think I'll make a little change. You make a little change, you hit the test button. You see the green bar go across the screen. Oh, everything still works. I'll make another little change. Hit the little button. The green bar goes across the screen. Yes, everything still works. You make another little change, and another, and another. You are not afraid to change the system. You've got a suite of tests. That test tells you haven't broken anything. It doesn't give you perfect confidence, but it gives you confidence with a few decimal places. So you are able to change the code. The code has become flexible. Why do we talk so much about architecture and design? Why are architecture and design important issues? And they are. And the reason we talk about architecture and design is because we want our code to be flexible and maintainable. But nothing makes a body of code more flexible than a suite of tests, by a huge order of magnitude. If you don't have a suite of tests and you're all worried about the design, you're worried about the wrong problem. Because what you really need is a suite of tests to make your code very flexible, and then you can tune that flexibility by improving the analysis and design. If you have a terrible design, but you have a suite of tests, you can change the design fearlessly. But if you have a great design and no tests, you're afraid to touch anything. That courage to make changes is more than enough reason to adopt test-driven development. That's the key to flexible systems. You want a flexible system, you get a suite of tests. But there's more. How many of you have ever integrated a third-party package? Okay, so the third party sends you this nice CD or something, and on there's all the code you need. Plus there's this nice manual, and the manual's written by some tech writer who describes how to do the third party thing. And at the back of the manual there's this ugly section with all the code examples. Where do you go? First place you go in that manual. You go to the code examples. Why? Because they'll tell you the truth. You don't want to read what the tech writer wrote because she's just paraphrasing what somebody else wrote. You want to go to the code. The code's going to tell you the truth. If you're lucky, you're going to go to that code section, cut and paste it out, put it into your application, and fiddle with it until it works. When we're writing unit tests, what we are writing are the code examples for the whole system. Little tiny tests that describe how some part of the system works. And those tests are written in a language that the programmers understand. They are completely unambiguous. They are so formal they execute, and they cannot get out of sync with the application. They are the perfect kind of design document. You want to know how to create an object? There's a test that creates that object, written in a language you understand. Shows you every way you can create that object, unambiguously. You want to know how to call an API function? There is a test that calls that API function with every possible argument it can be passed with every exception it can throw. You want to know how to work something in the system? You go to the test that describes how that part of the system works. These tests are design documents, the best possible kind of design document. They are so formal they execute. There's an old joke about agile development, about how it's all about not writing documentation. Baloney. In agile development, we write lots of documentation. It just happens to be very formal, so formal it executes. Completely unambiguous kind of documentation. It's written in the right language for system documentation. It's written in code. How many of you have ever written tests after the fact? You write some modules, then you write a little bit of code. How much fun is this? Generally, it's not very much fun because we've already gotten the thing to work. Yeah, we wrote the code, we ran a few tests, manual tests, we believe it works. Then, as an afterthought, we write a few unit tests. Okay, I'll test this, I'll test that. And then we'll get to some part of the code which is hard to test. You can't get into it. It turns on the X-ray machine, or it deletes all the rows in the database. There's some reason why you really don't want to call this function, or you can't call it. And you say, yeah, but I know it works, and you go on. You don't get nice, complete coverage. But when you're following those three laws, you must test every part of the system. So you design the system to be testable. It has to be testable because you're writing the test first. So you design the system to be testable. Another definition of testable is decoupled. The very act of forcing yourself to write unit tests around little tiny units forces you to decouple the system into little tiny testable units. So your design is going to be better simply by virtue of the fact that you're writing these tests. The litany of benefits goes on and on. You get all the documentation, you get the flexibility, you get the courage, you get low debug times, you get a better design. There can't be any reason anymore for not doing test-driven development. If you still think this is controversial, you're very wrong. The jury came in a long time ago. Test-driven development is a key practice for software developers. Software is a very sensitive discipline. And by that I mean, we could go out today and find a bridge somewhere and start removing bolts. The bridge probably wouldn't fall down. Well, if you took enough bolts out, it would, but you start taking bolts out, it's probably not going to fall down. We could go out and, I could get a gun and start randomly firing in the audience. I don't think I'd kill too many people. It might hurt a few. These systems are not very sensitive. They can suffer breakage. They can suffer small damage. But software is not like that. Software, I can reach into a 250 megabyte executable and flip one bit, and the whole system will crash. How is it that we have a discipline that is sensitive at the bit level, where most people don't? Most people have robust systems that can tolerate fault. But there is another discipline that has this same sensitivity. It's accounting. Accountants have this problem. A single-digit error at just the right time on just the right spreadsheet can take the company down and send the executives to jail. It's happened. So how do accountants deal with the fact that they have this sensitivity? They have a discipline. That discipline is called dual-entry bookkeeping. They say everything twice. Every transaction is entered in two places, once on the credit side, once on the debit side, and we do this magic subtraction on the balance sheet that should yield a zero. If it doesn't yield a zero, somebody's made a mistake somewhere. Test-driven development is a lot like this. We may say everything twice, once in the production code, once in the unit tests, and there's this wonderful execution that takes place that shows that everything works. How can we not adopt the level of discipline that accountants adopt? Acceptance testing. QA is stuck at the end of our processes. This is a terrible idea. We don't want QA stuck at the end where they're trying to constantly correct the errors we've made. We want QA brought to the front. What happens when QA is at the end? Do developers deliver on time? Hardly ever. Does the date change? The final release date change? Hardly ever. So who gets stuck making up the difference? QA. QA is stuck in the worst possible situation. All the slack time has been burned. The developers have delivered late. The date can't be missed. And so now QA is in this position where they have to decide what tests to run and which tests to ignore, and which tests they're going to have to run slow and which ones they're going to have to run fast so that they can get to the date on time. And this does not help quality at all. QA is stuck in a high-stress, tedious job that is fundamentally error-prone. What do QA people do? Who's got a big suite of manual tests in their company? Right? Big suite of manual tests. This is fundamentally immoral. Right? To have a great big suite of manual tests. First of all, it's stupid because any computer could run those tests. Why the heck isn't a computer running those tests? Second of all, it's error-prone. Imagine it was your job to run those tests. What do those tests look like? Enter P95QP into the username field. Enter GX972 into the password field. Click Login. Does the screen say, welcome? Check it. This is your job. And it'll be your job for as long as you're a QA analyst. How much do you care about this? We don't want people doing something that a computer can do. So I want to take QA and move it completely away from the back end of the process, move it all the way to the front end of the process. I want QA writing automated tests that do what we think they ought to be doing manually. I want them to write those tests, and I want those tests to become the requirements that the developers use to implement the system. QA and business together should be writing automated tests that define how the system works in excruciating detail, and that way developers know when they're done. What is the definition of done? How do you know when you're done? Yeah, you'd like to think it was when you were testing. So your boss comes to you and says, "You done with that?" "Yeah." How many times has that happened? Your boss comes to you and says, "When are you going to be done with that?" "A week or two." Week or two goes by, you done with it? "Yeah." We cannot trust the word of the developer to say that they're done. We don't want to make it a matter of just saying we're done. We want to have a definition for the word done. How many of you have multiple definitions for the word done? I've consulted for companies where they have one meaning for the word done and another meaning for the word complete. I had one company once where they had done and done. I don't want to have multiple words like this. I want done to mean one thing, done. And that definition is all tests pass. All acceptance tests, all unit tests pass. Then you know you're done. You are not done until then. In an agile environment, when do you decide you're done? When are you supposed to be done? At the end of every iteration. At the end of every 2-week period. Who's got 2-week iterations? Who's got 1-week iterations? Should be more. Who's got 4-week iterations? Too many of you. It should be 2 weeks or 1 week. We've figured out that 4 weeks is probably too long. Who doesn't have iterations? Need to have iterations. And at the end of every iteration, we want to be running the acceptance tests that demonstrate that we are done with the work items that we worked on that day, that iteration. Work ethic. Another aspect of professionalism. How many hours do you work? Software developers tend to work a lot of hours. Overtime is fairly common in our industry. But let's assume that overtime is not the issue. Let's assume that you work in an environment where it is safe to put in 40 hours for your employer. How many hours do you work? It should be more than 40. Not for your employer. You should work 40 hours for your employer. That's the professional thing to do. But you're not done at that point because there's something else that needs to be done. Your career needs to be enhanced. Your career needs to be taken care of. You are a software developer. It is not your employer's job to enhance your career. It is your job. So there are things that you need to learn. There are things that you need to do. There are books that you need to read. There are conferences that you need to go to. There are training courses that you need to attend. And it's not really your employer's job to do all those things for you. It's your job. Now, if you happen to work for an employer that does those things, well, that's good. But honestly, the responsibility is your own. You should be putting in another 20 hours a week just on yourself. You should be reading. You should learn a new language every year. You should be fiddling around at home with different language structures and different design structures. You should be enhancing your ability to do your job at all times. What kind of a doctor would you like to go to? You're sick. Do you want to go to a doctor who puts in 8 hours at the office and then goes home? Or do you want to go to a doctor who spends his evenings reading the journals and learning and going on his own dime to conferences and learning new techniques all the time? And it's obvious which one you'd like to go to. If you get sued, what kind of a lawyer do you want to have? Some guy who lives and breathes it, or a guy who considers it a 9-to-5? Again, it's the same issue. A professional does more than just 40 hours of work. Sorry, that's just the way it goes. If you want to be a laborer, you can work 40 hours. If you want to be a professional, it takes some commitment, it takes some time. You're going to have to learn on your own time if your employer doesn't do it for you. The books you buy, you should buy yourself. Oh, your employer can buy them for you if you want, but if your employer won't, you should buy them. The training courses you go on, it's nice to have your employer to send you on training courses, but you ought to think seriously. If your employer says no, you ought to think seriously about, well, maybe I should go anyway. Maybe I should pay for it myself. Know your field. Software development is a very rich field. There's lots in it. Just the last 10 years have been fertile with new ideas. But if you go back 20, 30, 40 years, we've got loads of ideas in this field that most people don't know anymore. So, for example, there are design principles that were identified in the 90s, things like the Liskov substitution principle and the open-closed principle and the dependency inversion principle. How many of you know these? Not enough of you. Right? These are important ideas. The design patterns, how many of you could describe a visitor pattern? Not enough of you. Right? We need to know these patterns. They're important. Imagine a hardware engineer who did not know his circuits. You would expect a hardware engineer to know their circuits. You would expect a hardware engineer to be able to draw an astable multivibrator if you told him to draw a tank circuit if you asked them to. We should know these things. How many of you could write the quicksort algorithm? Just off the top. A few of you. The rest of us don't know this. Fundamental algorithm, we should know it. We should have studied it. We should understand why it works. Not because we're ever going to have to write it again, but because there are ideas in there that are important for us to know. We should all know several languages. How many of you know at least 4? See, not enough of you. You should know more than 1 language, more than 2, more than 3. If you're working in Java right now, you should certainly know C++. You should probably know Python. You should probably know Ruby. There's a whole bunch of languages that you should know. You cannot survive in this industry unless you know a lot about it. Who knows what a data flow diagram is? Lots of you. That's pretty good. An old technique from the structured analysis days. We probably don't use them much anymore, but it's a good idea to know what they are. How many of you know what a Nash-Schneiderman chart is? A couple of you. Look at that. Old flow chart from the structured programming days. It would be a good idea to know what this chart looks like and why it was important in its day. How many of you know UML? Ooh, a bunch of you know UML. Of course, it's been important, although it's waned in its importance lately. But a good idea to know what this stuff is. Who's heard of Parnas tables? Got a guy over there who knows what Parnas tables are. A few of you. David Parnas, genius in our industry, wrote loads and loads of papers You should know what these things are. This is all, oh, by the way, who's read Structure and Interpretation of Computer Programs? Okay, now, the next book you read must be this book. It doesn't matter what else you've got on your reading queue. Put everything else aside. Go find this book. It was written in the 80s, I think. Structure and Interpretation of Computer Programs. Go out, get this book, and read it. It will fundamentally change your life. Software developers, in order to be professionals, have to engage in continuous learning, constantly learning new things. Because although we still do if statements, assignment statements, and while loops, we do them in strange, new, and different ways, new languages, new platforms, new ideas constantly. So the definition of a software developer is someone who is learning voraciously all the time, constantly reading, constantly learning new ideas. Read books, read blogs, read articles, read Twitter. Anybody read scanning Twitter all the time, looking for new links, looking for new ideas? There are guys on Twitter saying, hi, I just read this cool thing. You should know that. And then you ought to go read it too. Conferences, user groups. How many of you do lunch and learns? Good. It's always a good idea to do that. Get some idea to present, some guy to present some new idea every week at a lunch and learn. Go do book reviews through lunch and learn. Stuff like that. How many of you practice? By practice, I mean practice writing code. Do you sit down and just write an algorithm that you already know, just for the heck of it? Do you crank up your IDE and say, I'm going to do prime factors, and just write the algorithm for prime factors? To train yourself to make the right decisions, to train your muscles to move the right way, to hit the right hotkeys at just the right times. Other professionals practice, musicians practice, lawyers practice. We should be practicing too. We should have a set of exercises that we do. In the morning, we should wake up in the morning, brush our teeth, maybe go to work, pop open the laptop, and do a quick hello world, or a quick prime factors or something, just to warm up, a practice session. And one more topic, and then I'll open it up for questions. And that last topic is collaboration. How many of you do pair programming? Ooh, look at that. We got a bunch of people doing pair programming. That's cool. Right? Pair programming is the idea where we're going to sit and work together at a single workstation, working on the same problem together, two minds engaged in the same problem. And some people think, well, that would be inefficient. It would be difficult to do. We'd get half the code written. It doesn't seem to work that way. When two people work at one workstation, they seem to produce code at the same rate that two people working at two workstations do, for whatever reason. They just get the same amount of work done. It doesn't seem to hurt productivity at all, but it does enhance accuracy, and it does something else, something very important. Knowledge moves through the team. How many of you have a situation where Jim is the only guy who knows the database? If Jim gets hit by a truck, we're in deep doo-doo. We don't want to have that situation. Knowledge silos where only certain people know certain parts of the code. So we use pair programming and collaboration as a way to spread knowledge through the team. It is the responsibility of professionals to make sure that their company is not vulnerable to knowledge silos. And with that, I think I will stop talking and open things up for questions. Are there any? I see none out in the audience. Any from the, oh, yes?
You made the comment a couple times that techniques like CPE and pair programming actually save time. That's a huge hurdle when I'm not working with clients to try to convince them as a non-developer myself that these things actually do increase quality, increase throughput, all those kinds of things. Short of sitting down with somebody and demonstrating for them, how do you convince them?
So it's a very good question. And the question was, to paraphrase, if we accept that test-driven development, for example, saves time, how do we convince others that it does so? Answer is you don't. There is no way to convince others that it saves time. I could stand up on the stage like this and blather on, and you could nod your head and go, well, maybe, but I don't think so. The way we convince people is not by argument, it's by demonstration. I am a test-driven developer. If you were to work with me, you would be forced into test-driven development because I won't do it any other way. If you decided not to work with me but worked next to me anyway, you would notice that I was outdoing you. You would notice that I was getting things done faster and more accurately than you were. And you might, if you got over it, say, well, how is it that you're doing that? And I would show you. Now, this is a demonstrable thing. Test-driven developers produce better code quicker, more accurately than non-test-driven developers. So if you are a test-driven developer, your best chance at convincing people is to simply do your job and do it very well. Arguments aren't the thing. Oh, you should talk about it, certainly, but you're never going to convince anybody by talking. You will convince people by doing. That answer your question? Yep. Next. Someone in the back. Yep.
We have a couple of questions from the virtual audience. A follow-on to just the previous question about who should write the code for the unit tests. Would that be the developer themselves, or is overhead injected into the process if someone else is writing the code for the unit tests?
So the question was, who should write the code for the unit tests? Should developers write their own unit test code, or should someone else write the unit test code? And if so, is there some kind of overhead injected by having someone else write the unit tests? In general, developers write their own unit tests. We don't like to have acceptance tests written by the developers. We like to have them written by QA. But the unit tests are written by the developers because the unit tests are an expression of what the developer intends to do. So the developer writes the unit test describing what they intend to do, and then they write the production code doing what they intended. Also, the coupling between these two is so tight. You write a little bit of unit test and a little bit of code and a little bit of unit test and a little bit of code. It's virtually impossible to get the unit test written by someone else, unless you are pair programming. If you are pair programming, then you can play an interesting game. This is a game called ping pong. And in ping pong, one member of the pair writes a bit of a unit test, gets it to fail, and then hands it over to the next guy who writes the production code to make it pass. And then he writes the next little bit of a test to make it fail, and the first guy makes it pass. And then he writes the next test, and so on. So it's a game. And the game can get pretty interesting, like, pass this sucker. So it can be a kind of a fun game to play. In general, that means that you have two brains deeply engaged in two different aspects of the same problem. It turns out to be very effective. Next. Yep. Okay.
Continuing the thread from the virtual audience on test-driven development and unit tests written by developers, there's a question about what's the best strategy for TDD when extending an existing system?
Yes, the legacy code problem. The question was, if you've got an existing system that was not done with test-driven development, how can you then start to do test-driven development? Okay, so the first thing you have to do is get Michael Feather's book, Working Effectively with Legacy Code, and read it. And when you're done reading it, you will be horrifically depressed because the answer is it's really, really hard. Now, that doesn't mean you don't do it. But it does mean that you shouldn't have any false illusions. It took years to make the mess you're in. It's going to take some time to dig out. Basically, what we do is we first of all admit there's no way we're going to write tests for everything in this system. The legacy code is never going to get completely under test. But maybe we can write just enough tests to stabilize it so that when the tests pass, we are confident that this system is working. So we do that by every iteration looking at the new work that needs to be done. If that new work is independent, we write tests for it according to test-driven development. If the new work is in the legacy, then we try to find just small areas in that part of the legacy code where we can write a few stabilizing tests, and then we continue. Over the months and years, enough tests will accumulate in the legacy environment to stabilize it to the point where we are relatively confident in it. There is no magic bullet here, right? It took a long time to make the mess. There's lots of code that's going to remain untested, but you can at least get a handle on it. And keep in mind that every time you write a test in the legacy environment just gets a little bit easier to deal with, every single time. So that you get this nice incremental improvement. Yes?
Bob, this was a great talk. I want to start with a confession. I'm a software development manager who got past security and snuck into the session. And I'm wondering, what can I do as a development manager to encourage my team to adopt some of the professionalism that you talked about?
Yes, okay. So first of all, you cannot dictate it, and you obviously know that, right? So the question was, to repeat the question, as a software development manager, how can I get my team to start adopting professional behaviors? And the answer to that, again, is the same as before. If you're a manager and you want your team to behave professionally, then you behave professionally. You do this by becoming a role model, becoming an example. Now, your job is fundamentally different from theirs, but if you are taking your job seriously and obviously behaving professionally, that will carry over. Now, there's nothing wrong with a manager also asking the questions. How do you know this code works? What have you done to test it? Do you have a suite of tests that you can demonstrate to me that this tests the code perfectly? What are your code coverage numbers? I never want a manager dictating code coverage numbers. If a manager comes along and says, no code will ever get through our system unless it's got at least 70% coverage, then by God, we will get 70% coverage, and that coverage will be meaningless because people will write tests without asserts. So we don't want to have that kind of dictating scheme. We do want to have a scheme where the managers are constantly acting professionally themselves,